So we've been talking about triangles. So here I'm going to draw a mini version of a triangle, a medium-sized version of a triangle, and then an enlarged version of a triangle. So let's say all of these are right triangles, so they all have 90-degree angles. And let's also say that they all have a 20-degree angle as well. Okay, so I got three triangles. They all have a 90-degree angle, and they all have a 20-degree angle. So what's true about these triangles? Yeah, they're similar. Good. Because two congruent angles is enough to prove that triangles are similar. So that means that if you take this triangle and just enlarge it a little bit, you'll get the medium-sized one. And then if you enlarge it just a little bit more, you get the large triangle. They're the same shape, they're just different sizes. Okay, so that means they all have the same angles. What else is true about similar triangles? Besides all the angles being the same. What's true about similar triangles? Are the sides equal? Clearly not, right? Because this is a lot shorter than that. What is true about the sides? They're proportional. Good. So the sides are proportional, which means that the side fractions are equal. So we've got three triangles, and all the fractions are equal. So that means that this fraction will equal this fraction will equal this fraction. Okay, so all of that we've talked about before. So here's the new thing. Since all of these fractions are equal, there's a name for that fraction. So the terminology is important. That's what we're learning today. So this fraction equals this fraction equals this fraction. And because all those fractions are equal, we can give it a name. And the name is sine. S-I-N-E. That's the name for this fraction. And since the angle is 20, it's the sine of a 20-degree angle. Because if that angle was different, then the fraction wouldn't be the same. And then we abbreviate it S-I-N. The word is actually sine, and then for some reason we tack off one of the letters and abbreviate it S-I-N. So this is the terminology we're learning today. It looks terrible, but it's just the name for a fraction. It's this fraction. All right, so that's our preview. Now we're going to put some information down on a note card to make it less scary looking, but it's not as bad. It's not as bad as it looks. It's just a fraction. So here's the note card. This is number 62. Everything on this note card has to do with right triangles. And it has to do with right triangle fractions. So there's a bunch of terminology that we're going to learn. First one is called opposite. An opposite is the leg across from the angle you are talking about. The leg across from the angle you are talking about. So now let's draw a triangle on the note card. And it's a right triangle because everything we're talking about today just has to do with triangles that have a 90-degree angle. And let's say this angle here is 50 degrees, and let's say that one is 40. And then the sides, let's call them X and Y and Z. So there's the triangle we're going to refer to. Okay, so first let's focus on 50. What is the side that's across from 50? I'm asking for the side across from 50. Now, in first period, a couple people said 40. The reason that was wrong is 40 is an angle. 40 is across from 50, kind of. But 40 is an angle. We're looking for a side that's across from 50. So the side that's across from 50 is X. You all right with that? So that's the opposite of 50. So opposite 50 is X. Because that's the side that's across from 50. Okay, but now let's shift our attention to 40. Which side is across from 40? Y. So Y is opposite 40. So opposite 40 is Y. So opposite is a little bit confusing because it changes depending on which angle you're talking about. If you're talking about 50, then X is opposite. But if you're talking about 40, then Y is opposite. So that's why it says it's the leg across from the angle you're talking about. So that's opposite. Then the next word is adjacent. Adjacent is the leg next to the angle you're talking about. Adjacent is the leg next to the angle you're talking about. All right, so let's refer to 50. Let's talk about 50. What is the side that's adjacent to 50? So we're looking for a side that's next to it. Now Z doesn't count because it's the hypotenuse. So it's Y. Y is adjacent because it's the leg that's next to 50. So adjacent to 50 is Y. And then if you shift your focus to 40, adjacent to 40 is X. So adjacent is also a little bit tricky because adjacent changes depending on which angle you're focusing on. If you're focusing on 50, then y is adjacent. But if you're focusing on 40, then x is adjacent. Same thing with opposite. If you're focusing on 50, one side is opposite. If you're focusing on 40, the other side is opposite. Okay, now here's the good news, though. Hypotenuse never changes. So z is the hypotenuse. It doesn't matter which angle you're referring to. Z is across from 90, so z is hypotenuse. So opposite and adjacent can change depending on the angle you're referring to, but hypotenuse doesn't change. It's z in this picture, always across from the 90. Okay, so then our focus today is fractions. So remember those three triangles I showed you, the mini one, the enlarged one, and the really big one? There could be a mini version of this one that had a 40 and a 50 and a 90. Or there could be a really big version of this one that has a 40 and a 50. So picture the mini version of this triangle, the medium-sized version of this triangle, and the enlarged version of this triangle. They're all similar. Since they're all similar, all their fractions are equal. And so because all their fractions are equal, we have a name for those fractions. And one of them is sine. So let's write that down. The sine of an angle. So this looks terrible. SIN, something you've not ever seen in math before. But simply, it's a fraction. So when you see these three letters and an angle, don't panic, just think fraction. And the sine fraction is opposite over hypotenuse. So if you're looking here at 40, then the sine is this fraction. And there's a mini version of this triangle, and there's an enlarged version of this triangle. This fraction is going to equal that fraction, is going to equal the mini fraction, because all those triangles are similar. So that's why we can have a name for this, because it's the same in all pictures, because they're all similar. Okay, then there's another fraction called cosine. It's spelled C-O-S-I-N-E, but we abbreviate it COS. So this is the cosine. And the cosine is adjacent over hypotenuse. And then the last fraction is tangent. It's spelled T-A-N-G-E-N-T, but we abbreviate it T-A-N. And the tangent of the angle is opposite over adjacent. Okay, so all this terminology looks terrible. It's a lot of new stuff for you. SIN, COS, TAN. Don't let that throw you off. All it means is, please give me a fraction. And I guess I'm putting the please in there because math isn't always polite, but I'm trying to be polite about it. So sine and cosine and tangent, all they're saying is the answer is a fraction. So when you see these letters, you're going to give fractions as answers. Okay, of course, you're going to have the note card when you're taking tests in this class, but this shows up a lot on the ACT, and it'll show up on the state test. So I want to show you something that'll help you remember all this. So I'm going to underline the S and the O and the H. And then I'm going to write those letters down here. So that stands for sine, opposite, hypotenuse. And then the C and the A and the H go together. So I'm going to write that next to it. So I just got that from the C here, the A here, and the H there. And then the T and the O and the A could be put together. So I'm taking all this information up here and kind of condensing it. So this is sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite adjacent. Kind of all together in one condensed area. And I don't know if this is a word, but if you wanted to pronounce it, you could pronounce it SOHCAHTOA. Anyway, maybe that'll help you remember, maybe it won't. Like I said, you'll have this note card on the tests in here, even the final exam, but these fractions come up a lot on the ACT, and they will definitely come up on the state test. So it would be good to memorize that for all of that stuff. All right, that's it for the note card. Here's the hole punch for you. So of course you need a sheet of paper. Today's paper is called Geometry 8-3 Day 1. You don't need to draw these triangles.
What question is this?
Well, so far I haven't asked the question. We're actually going to start with number 1, which is rare. So, yeah. Don't need to draw these triangles. I'm just showing them up here for visual effect so you can see what's going on. So, what's true about all these triangles? Yeah. They're similar. Good. We got a mini version, a medium version, and an enlarged version. All these triangles are similar because they share 2 angles. An angle-angle similarity is enough to prove that triangles are similar. Okay, so since they're similar, that means that all the fractions are going to be equal. So I'm going to measure the medium-sized one. And this measures, and it's 16 centimeters maybe. And this is 30 centimeters. And this is 34 centimeters. Okay, so here's the question on number 1. Question number 1 asks for the sine of 62. All right, so don't think too deeply about it right now. What is sine asking for? Yes?
Isn't just a fraction of 60.
It's asking for a fraction. Good. So our final answer is going to be a number on top and then a number on the bottom. Just like probability asks for a fraction, sine asks for a fraction. Okay, but sine asks for a particular fraction. It asks for the fraction, please put the opposite on top, and then the hypotenuse on the bottom. Okay, so let's look at this triangle. Hypotenuse is probably the easiest, so what's the hypotenuse?
16.
No.
34.
34.
I thought you were just pointing at 16 like it was the answer. So I got
Yes,
confused.
yes, sorry, I didn't mean to throw you off there. I wasn't trying to trick you.
34.
Yeah, so across from the 90 is the 34, right? So 34 is the hypotenuse. So that goes on the bottom of the fraction. Because the new thing we learned today is that the sine fraction has hypotenuse in the denominator. Okay, then it has opposite in the numerator. So let's look at the 62. And what's opposite from 62? 30, right? You with me? So the answer to number 1 is 30 over 34. Is everybody okay? Okay, now let's pretend that this triangle is twice as big as this triangle. Then this would be 60 instead, right? And this would be 68. So in that case, then the sine would be 60 over 68. But 60 over 68 reduces to 30 over 34. So that's why we don't care which triangle we look at. They're all similar, so all the fractions are going to be equal. So they're not saying how big the triangle is because they don't need to. The sine of 62 is going to be the same fraction no matter what size the triangle is, because all these triangles are similar. Okay, number 2 is asking for the cosine of 62. So the cosine fraction, well, it's a fraction first of all, right? Here's my cosine fraction. Hypotenuse still goes on the bottom, so 34 is on the bottom. And then, but this time adjacent needs to go on top. So let's look at 62. And what's adjacent to 62? Yes? 16 is next to it. It's the side that's next to it that's called adjacent. 34 is next to it also, but it doesn't count because it's the hypotenuse. So 16 is adjacent. So the answer is 16 over 34. All we're looking for is fractions. Sine, cosine, and tangent, they seem complicated, but all we're looking for is a fraction. So tangent of 62 is question number 3. So what's the tangent of 62?
over
30 over 16. Awesome, Charlie. Everybody see where he got that? So here's 62. Opposite is 30. Adjacent is 16. And the tangent fraction says put that number over that number. Opposite over adjacent. So that's why it's 30 over 16. Okay, there's another angle in this picture. It's this angle. How can I figure this angle out? Yeah.
62 plus 980, and then subtract that from 180.
Yeah, so the fact he's using is all 3 angles in every triangle add up to 180. So we already have 2 of them, so we can subtract them from 180. It turns out it's 28. So this angle's 28. So now I'm going to ask for the sine. This is number 4. I'm going to ask for the sine of 28 instead. So now I've shifted my focus, and now I'm looking at 28 instead of 62. So the sine is the opposite. So here's 28. What's opposite from 28? 16. So the sine of 28 is 16 over 34. So now we're going to look at the cosine of 28. Cosine is adjacent over hypotenuse. So here's 28. Adjacent to that is 30. And then hypotenuse is still 34. So cosine of 28 is 30 over 34. What do you think question 6 is? Tangent of 28, good. Tangent is opposite over adjacent. So that is, well, opposite from 28 is 16. Adjacent to 28 is 30.
16 over 30.
Good, so 16 over 30. All right, now I'm going to draw another triangle. We'll look at this one instead. So it's still got a right angle. Everything we're talking about today has to do with right triangles. This side is 20. This side is 12, and this side is 16. Okay, then in this corner, there's a circle with a little line through it. You've never seen that symbol before. Yeah, it's crazy looking. This symbol is a Greek letter. It's called theta. Theta. So in math class, sometimes we use Greek letters to represent angles. So that's what's going on here. This is the angle. Over there I had 62 and 28. But here I've got theta. And it just represents what that angle is. And then there's a thing in this corner that looks like a B, but it has a little tail on it. It's another Greek letter called beta. So don't let these letters throw you off. I could use X or Y, but it's tradition in math to use Greek letters for angles. All right, so number 7 is asking for the cosine of theta. So when you see COS, what's the first thing you think?
Adjacent over hypotenuse.
Fraction is the first thing you think, but then the next thing you think is, I need to put adjacent on top and hypotenuse on the bottom. But don't think about all that at first, because it's intimidating. When you see COS, just think fraction. And then worry about what fraction it is later. All right, so what is the hypotenuse in this picture? You know this. What's the hypotenuse? It's 20, because that's 20 is across from the 90. Now this triangle is a little bit different than the one over there. I turned it, right? But 20 is across from 90, so that's why 20 is the hypotenuse. Okay, then we're focusing on theta. Adjacent to that is 12, because it's next to the theta. So the cosine of the theta is 12 over 20. Okay, number 8 asks for the cosine of beta. So now we're going to shift our attention to this angle. Adjacent to this is 16. That's the tricky thing. If you're looking at this angle, adjacent is 12. But if you're looking at this angle, adjacent is 16. Hypotenuse doesn't change, though. That's nice. Hypotenuse is still 20, no matter which angle you're looking at. Is everybody doing okay? Okay, I'm going to skip forward to number 14. So there's a different triangle in number 14. Here's the triangle in number 14. And the question is asking for the sine of the theta, for the cosine of the theta, and for the tangent of the theta. So which one of these can we figure out based on the information given? Let me take a step back. Here's the 90. So which two sides do we have? Do we have the opposite? Do we have the adjacent? Do we have the hypotenuse?
We just have the adjacent.
We have the adjacent to theta, and then we also have the hypotenuse. Okay, so which one of these uses adjacent and hypotenuse? Cosine. So the cosine is 1/2. All right, but we can't figure out the sine or the tangent yet because those use the opposite, and we don't have the opposite. How could we figure out the opposite? Yeah, Pythagorean Theorem, right? Any right triangle, the leg squared plus the leg squared equals hypotenuse squared. So let's call this, let's just call it x, because we don't know what it is. So x squared plus 1 squared equals 2 squared. Because leg squared plus leg squared equals hypotenuse squared. So x squared plus 1 equals 4. So x squared equals 3. So x is the square root of 3. So now we figured out that this side is the square root of 3. So now we can answer these questions. Sorry, I wrote that down kind of quick. All right, so the sine is opposite of our hypotenuse. So that's root 3 over 2. And then the tangent is opposite over adjacent. So that's root 3 over 1. And you could just write that as root 3. Because dividing by 1 doesn't really do anything. Does anybody recognize this triangle? The hypotenuse is twice as big as this. And this is this times the square root of 3. What triangle has a hypotenuse that's double one of the legs and a leg that's square root of 3 times the other leg? Yeah, the 30, 60, 90, right? So this is a 30, 60, 90 triangle. Turns out theta is 60, and that's 30. I'm just bringing it in last week to jog your memory over the weekend about the 30, 60, 90s.